Okay, guys, this is a screencast for the benefit of anybody that was not actually present in person in class on October the 22nd, because we walked through this paper during class and we did most of this together. So we're going to start with this top graph that says density of noble gases. What we are starting to look at are things known as periodic trends. Periodic trends are things that we can see that change in a predictable way as you either move down a column or group on the periodic table or as you move across a period or a horizontal row. If you think back to the periodic videos that we looked at earlier this week, you saw lithium reacting with water, sodium reacting with water, potassium reacting with water, and rubidium reacting with water. And if you watched those videos during the daily check-ins from earlier this week, you noticed that as you went from lithium to sodium to potassium to rubidium, the violence of the reaction increased. So lithium is the lightest, smallest of our alkali metals in column 1 on the periodic table. And it sat there and sizzled and bubbled and whatnot when it was in the water reacting. And then they moved on to sodium, and sodium was more violent a reaction than lithium. And then they showed the one with potassium, and they dropped it in there, and it basically caused a little bit of an explosion, and it went everywhere. And then they showed rubidium, which was really violent. So that's actually a periodic trend. As you went down the column from lithium to sodium to potassium to rubidium, the violence of the reaction increased, okay? That's one periodic trend that you've actually already seen without us really talking about the fact that it was a trend. And we're going to start looking at some other ones. You're actually going to have a lab coming up where we're going to look at some other periodic trends. The lab portion is going to be you measuring the density of a couple of different elements, and we're going to look at the periodic trends of a certain group of elements. All right, but anyway, we're going to look at some periodic trends. We're going to start with this particular graph. So first of all, anytime, any graph, one of the first things you probably need to do is take a little bit of time to read the title and to look at what's on the x-axis and the y-axis. Remember that the x-axis is your horizontal axis, your y-axis is your vertical axis. So on this particular graph, sorry about that, we have two variables. The x-axis variable is density, and the y-axis variable, it just gives us some chemical symbols. Well, helium, neon, argon, krypton, xenon, and radon, those are all your noble gases. This is column 8A or column 18 on the periodic table. And they're actually listed by increasing atomic number. Okay, so our two variables are density on the x-axis right there, and the other variable is going to be the atomic number of our noble gases. I'll just put a number symbol. Atomic number of noble gases. Because they aren't listed over here just randomly. So atomic number increases as you go down. So if you look on the periodic table, you notice that helium's atomic number is 2, neon's atomic number is 10, argon is 18, krypton is 36, xenon is 54, and the atomic number for radon is 86. So the atomic number is increasing as you move down the column. Okay. So next thing I want you to do is to make a generalization about the graph. Well, what do I mean? Well, let's go back and talk about what we saw with lithium, sodium, potassium, and rubidium when we watched those videos. A generalization that can be made is that as you move down column 1, the reactions got more violent. That's, in general, a true statement, okay? Because lithium was highest in column 1, and then followed by sodium, followed by potassium, followed by rubidium. So as you move down column 1, the reactions got more violent. That is a generalization. It tells me how those two variables are related. What two variables? The atomic number, or the size of the alkali metal that we're looking at, and the violence of the reaction. Here, we need to make a generalization about the two variables that we have in this situation, and that is density and the atomic number of the noble gases. If you notice, the smallest atomic number also has the smallest density. And as the atomic number gets bigger, well, so does the density. Okay? So a generalization that we can say, or that we can make, is as the atomic number of the noble gases increases, density increases also. Okay? So our generalization is going to mention how both of these variables are related to each other. Okay, so here's my generalization that I made. As atomic number of the noble gases increases, density also increases. And you'll notice that I made sure that my generalization included how my two variables were related to each other. Okay? As one does this, the other one does that. All right, let's try another one. All right, here we have another graph. The title of the graph is Trend in Atomic Radius of Group 2 Elements. Well, the title already tells me a lot about what to expect on the X and Y axis. And I go down to the X and Y axis, and sure enough, I have Group 2 elements across the X axis, and I have atomic radius along the Y axis. Now, I want to point out that the group 2 elements are listed not randomly, but they are listed in order of increasing atomic numbers. So if you look at group 2 on your periodic table, you'll notice that beryllium is the smallest, followed by magnesium, then calcium, then strontium, and then barium is the one with the highest atomic number. Okay? So we're going to write down our two variables. So one of them is your group 2 elements by atomic number. And also down here, just for clarification, I'm going to draw an arrow and put increasing atomic number. Okay, and then my other variable is atomic radius. And the little NM right there just stands for nanometers, which is a really, really, really small measurement. Okay, so my two variables are the atomic number of my group 2 elements and atomic radius. So again, I'm going to make a generalization that tells me how those two variables relate to one another. Okay? I'm going to follow basically the same format as I did up here. As this variable does whatever, this other variable does whatever. Okay? So as atomic number of group 2 elements increases atomic radius increases also. Okay. So, does my generalization talk about both of my variables? And the answer to that is yes, it does. I said atomic radius increases. My other variable was the atomic number of group 2 elements. So, I have told you how these two variables relate to one another. Basically, as you go from beryllium down the column to magnesium to calcium to strontium to barium, the atomic radius is getting bigger as you go down the column.